Well, hello and welcome to this artificial neural network in machine learning, or ANIMAL for short. This talk is split into two sections. Firstly, the rationale of what we did and why we did it. And then we move along from a documentation study into a real into the animal, which is an Excel-based neural network consisting of 10 neurons. Fine. So first of all, what do? We looked at the human brain. The human brain has had 66 million years of development, and we thought, well, what else can we learn from the neural networks in the brain that we can copy, basically? We all know we can copy the neurons, but what about else? What about the strategic intent of the various elements in the brain? Can we learn anything to apply and use in Excel? Well, in actual fact, we could. We looked at the cerebellum, the brainstem, the cortex, all these various issues, and the reason we did all this is because we had a project, and the idea was to try and minimize the maintenance support and to be proactive in the support by providing neural networks to recognize a pattern of failing well. So, with that in mind, we started to look at the upper brainstem, Medula Oblongata. It plays an essential role in passing messages between the spinal cord and the brain. Now, that is never really discussed in any of the neural networks, whereas this is our version of the Medula Oblongata. It looks at all the flow to and from the brain, the brainstem and everything else, and this looks at all the mechanisms, all the information flow and the activities of the neural network. So that's our take on that. Now it says the cerebellum is it's good at walking, distance measurements, alternative movements, and these are learned activities but are performed almost automatically under normal conditions. And you think, well, how does a spreadsheet do that? Well, the obvious way is activities in its own VB macros. It has macros in it, and so that's what we said. That's the cerebellum. Okay. Now the learning functions, obviously, the fulcrum of the learning functions are the neurons themselves. Now these are normally drawn with little circle diagrams, inputs, outputs, weights, biases, etc. So that was relatively straightforward. What we looked at was the synaptic shrinkage. We found that when you're looking at neural networks, you can look at false minima. It can find false minimum, and it freezes there. Well, the best fit is actually a little bit lower down. So synaptic shrinkage is what happens in humans when we turn off or repurpose neurons at a very early age, when we're learning, when we're most adaptable and learning. Basically the face of our mother. We recognize other faces as well, but we soon learn to look at people's faces. They're far more important than anything else, other faces. So that's when synaptic shrinkage takes place. And so we got a little synaptic shrinkage matrix, and you'll see this in the spreadsheet, to turn them on and off. Right, what else did we learn? Well, the surface area of the cerebrum is significant. The brain goes to great lengths to make the surface area much larger. So why? Don't quite understand particularly why, but we copied it. Rather than little circles in a spreadsheet diagram, we expanded that to be a complete neuron in its own right, with its inputs, its weights, its the bias, synaptic shrinkage. I'll come on to that in a minute, and it's all in that package. So rather than have a circle, we have that. In addition to that, we looked at the standard nerves, and you think, well, here we are, here are the inputs, and the axioms and the nucleus. This is the nucleus, and then it's the synaptic terminal, the outputs, and that's the outputs that goes there. Now, what we found is that this is really, really helpful in fault finding. It becomes obvious when you look at all these nodes or these neurons, when you look at them all, and they've all got figures in them rather than embedded into a single cell of a spreadsheet with hidden formulas behind it. This makes them explicit and very simple to understand and very easy to diagnose. However, we also recognise something else which was intriguing. We haven't seen it in the documentation anywhere else at the moment. That is that one particular neuron can feed another particular neuron, not once, but many times. And so you think, why? We only have one output from it, normally have one output from a neuron, but why does it feed another neuron many times? So this seems to suggest to us that the synaptic terminal, it doesn't modify the signal, but the fact that there are more connections to one particular neuron than just one, duplicate connections, means that maybe that output is more significant, and therefore more synaptic terminals end up in that neuron, in that receptor neuron, and therefore it learns that. So we postulate here, not only is there synaptic shrinkage in a younger brain, but there is also synaptic expansion. So we're looking at modifying the shrinkage to make it an expansion as well. Now, this is one of the first networks that we looked at. Here we have the input splitter, and the individual neurons. And as you can see, we can see everything in there, all the equations, and it's very easy. And then we come up with the outputs. Now, one thing that we should really mention is this is where we started to consider neural networks as a child's game, because it's like a jigsaw. The old jigsaw thing, we just copy and paste as many as we want wherever we want, and all the detail is in linking these inputs and these inputs to these outputs, and so it's just purely linking to it, click and go, so it's very simple. Once we've got this basic piece of jigsaw. Right, data entry screen. Yes, and this is what we're learning from the brain itself, but let's not go into that document at the moment. Okay, so that really summarizes the effects of looking at the brain. We found the major oblongata, the upper brainstem, in the form of the flow menu, cerebellum in the form of visual basic macros, cerebrum, artificial neural network, of course. Oh yes, we talked about the two hemispheres, the corpus callosum. Really, we haven't got two hemispheres, of course, we've only got one, but we can time multiplex and use the same hemisphere more than once if we need to. The folding of the grey matter and the gyri and sulci increase the real estate of the spreadsheet cells, which we've seen come up with this jigsaw concept, and the synaptic shrinkage, occasionally switching off some of the artificial neurons, but we've also done it to synaptic expansion as well. Right, that's in a summary what we have come up from our analysis of the brain. Okay, right, that's it. Cheers. Now we get on to the practical side.